All right, so the exam is due by midnight tonight. It's 31 questions, fill in the blank and multiple choice, a combination, and you have a 2-hour time limit. I would make sure that you have your calculator ready, any handouts, especially that Vesper handout that has all of the molecular shapes. So I would have your electronegativity tables with your common polyatomics, and then also this guy as well.
Wait, that sheet first review, I don't have that.
You don't have that one? Okay. It is posted on Blackboard, but
Okay.
a hard copy is a little nicer to have
Yeah,
come exam
I
time.
need a hard copy, I think.
So I would have all this stuff just handy and ready for when you start, so you're not spending time trying to find stuff. Is there anything else I wanted to say about the exam? I don't think so. So, since some of it's multiple choice, I do go back through and check your answers for, or not multiple choice, for the fill in the blank ones, because I don't want anybody getting it wrong just because of a formatting issue. So you can also send me an email if you think you got it right, but maybe you just put an extra space where there wasn't supposed to be one, it'll count it wrong. But I have been going and checking, and for the most part there are a few people who get points back because they just put an extra space where they didn't need it and it didn't read it as the correct answer. So I do double check those for the exam. So what we're starting on Thursday and Friday, depending what section you're in, is chapter 4. Chapter 4 is a really big chapter, so we split it into 3 parts, and the next exam that we take is just on chapter 4. So I already have the PowerPoints for the first part up, and then we'll be working through some problems on Thursday and Friday, depending what day you have class. So I'll have those posted by Friday at the latest, so that you can work on the questions and have them done Sunday. All right, so with the due dates all in mind, let's look at a problem. So this is a similar problem that you might have seen on the practice exam. If you haven't taken the practice exam yet, I strongly encourage you to do so, because the problems are in the exact same format. It's just different molecules that I'm asking you to answer about. Okay, so someone had asked a question about this: what's the difference between individual bonds and the molecule as a whole? So given this chemical formula, so CCl4, let's name it for fun because you might have to do that as well. So is this a covalent or an ionic compound? So covalent is where we're sharing electrons, and it's usually between a nonmetal and a nonmetal, or a nonmetal and a metalloid. Ionic is where electrons are transferred, and that's usually between a metal and a nonmetal, or a metal and a polyatomic. So what type of elements are carbon and chlorine? Non-metals, so this is going to be covalent. Okay, so when it's covalent, the key is using prefixes. So how are we going to name this guy? We look at the subscripts to figure out the prefix. So since there's no subscript after carbon, how many carbons are there? Just 1. So when we name it, since carbon, there's just 1 of them, we don't put the mono because it's the first element present. Okay? If there was 1 of the second element present, we would include the mono, but not on the first. That's when we talked about carbon monoxide, for instance. We didn't use mono on the carbon, but we did on the oxide portion. So we have just carbon for the first element. Now we have chlorine. So we're looking at the number 4 to figure out the prefix. So what's the prefix for 4? Tetra. Tetra, and then chloride, yes. So don't forget that IDE. So that would be the correct name of it. But the question's asking, my individual bonds are blank. And in the blank, you would write either polar or nonpolar. Then it says the molecule as a whole is, and then once again, polar or nonpolar. So when they're asking about the individual bonds, they're asking about just the bonds between carbon and chlorine. Because if I were to draw this, I would say carbon's my central atom. And that means that all my chlorines would go around it. So the individual bond they're talking about is between carbon and chlorine, because that's the only bonds present in this molecule, are carbon-chlorine bonds. So to figure out that polarity of just that bond, you're doing that electronegativity, that subtraction, using your electronegativity table. So you would find carbon and chlorine and then subtract their values. What do we have for carbon? 2.55, and then chlorine 3.16. 61? 0.61?
Yeah.
Right.
0.61.
0.61. So when you subtract them, these are absolute values, so that's why it's still a positive. You're comparing this value after you do that subtraction to that chart, where between 0 and 0.5, this is nonpolar. If it's above 0.5 up to 1.9, it's polar. So this value, 0.6, it fits in the polar region. So the bonds themselves, the individual bonds, are polar. When you're approaching the molecule as a whole, so if it's saying, is the molecule polar or nonpolar, they're talking about everything together. So that's when you need the Lewis structure and you apply those rules. The rules where if there's a lone pair on the central atom, it's polar. If there's no lone pair and all terminal atoms are the same, it's nonpolar. So when they're asking about the molecule, you're drawing the Lewis structure, you're applying the rules.
Nonpolar.
In this case, it's going to be nonpolar. We didn't even finish the Lewis structure, so how do you know that?
All the terminal atoms are the same.
Right, all the terminal atoms are the same, and carbon right now, with those single bonds, has 2, 4, 6, 8, and that's all it wants. So carbon's happy, which means it has no lone pairs on the central atom. It just has single bonds. So no lone pairs, and terminal atoms are the same. So that means it fits under the nonpolar. So I wanted to show this example because you can have polar individual bonds, but the molecule as a whole can still be nonpolar. These don't always have to be the same. You need to do the separate steps to figure each one out. Calculation for the individual bonds, Lewis structure for the molecule as a whole. All right. So that's the only question that I was posed via email. Do you guys have any questions on maybe the practice exam or some of the questions in the video, since we didn't have class on Monday? Maybe it makes sense.
I just ran into all. Can you just make up some that you thought was confusing? Sorry, I got bands on my braces.
Okay, fine. So this was slightly confusing to some people. So let's do bromine. And I'll explain why. How many valence electrons. Here was a multiple choice one that some people found confusing. So how many valence electrons? And here are your choices. Because sometimes multiple choice makes it more confusing than if you just read the answer. So let's say we had 3, 5, 6, and 8. So a lot of people want to pick 8. And I think the reason is because all atoms want 8 electrons, okay? But it's not asking how many electrons, how many valence electrons nitrogen wants. So 8 is incorrect, okay? 8 is the octet rule, that's how many it wants, but it's saying how many valence electrons does nitrogen have? So to figure out how many it has, right, you're looking at the periodic table. Make sure you have your periodic table all ready when you take the exam too. color code it, write on it, make your life easy. So you're gonna look and find where nitrogen is, and it's in group 15. Everybody in group 15 has 5 valence electrons. So the actual answer is 5. If I drew the Lewis dot structure of it, I would draw N, the nitrogen symbol, and I would draw 5 dots around it. 4, 5. Okay, looking at the Lewis dot structure, how many bonds does nitrogen like to make?
3.
3, yeah. So how many bonds does it like to make? You're looking at unpaired electrons. And we have 1, 2, 3 unpaired, because over here we have 2 paired up, so those ones don't count. So that means it likes to make 3 bonds. We actually see that quite a bit. Oh, I did have another question from somebody. It's just coming to me. So let me draw this guy again that we just looked at a minute ago. Where they asked, it was in the discussion part, how do you know when to do a dash and a wedge? So this comes when you take a Lewis structure and then use your molecular shapes and Vesper packet, which by the way, you have a color-coded one at the end of your lab manual, if you prefer one that's not kind of grayscaled. So it might be a little bit clearer. It's in the appendix of your lab manual, if you prefer to use that one instead. But they asked, based off of this Lewis structure, when you draw the molecule portion, how do you know if you have the dashes and the wedges? When do you do that? Okay, so let's look at this one. And for this one, to figure out its shape, you want to count how many things are around the central atom. So atoms count as a thing, and a lone pair counts as one thing. So how many things do we have around carbon?
4.
4. Each of these atoms count as 1, so 4 total things. So you're looking under the 4 comma area. And you have 4 different choices. So I'm looking on page 4 if you have the handout that I gave or printed it off. And there's a 4 comma 0, a 4 comma 1, 4 comma 2, 4 comma 3. So those are your choices. So what comes after the comma is how many of those 4 things are lone pairs. So in this case, do we have any lone pairs on carbon?
Oh.
No. So it's going to be 4 comma 0. So to figure out the shape itself, this tells you 4 comma 0 that that's going to be tetrahedral. And then it shows you how to draw it. I wanted to make it a little more clear, so I made a little molecule of it. So this would be what this actually looks like in 3D. It's a tetrahedral shape. So how they have to draw this, since it's 3D, since not all of the molecules are in the same plane, how they draw it, let me see how they have it. So they have it this way. Okay. So if I were to put a piece of paper here, well, the reason I'm doing the paper is because I'm trying to see which molecules are in the same plane. So notice I have this chlorine, the central black carbon, and then this white chlorine. These 3 molecules are all in the same plane. So to draw the ones that are in the same plane, those are just solid regular lines. So that's this part here. Okay, that's these 3 molecules that fit in the same plane. But now I have a molecule, a chlorine atom, poking out of the plane. And then if you look back here, if I turn it, the other one is going into the plane. Okay, so in order to draw the ones that aren't flat, aren't in a 2D structure, I need to indicate those with dashes and wedges. So the one poking out of the plane is going to be a wedge. Solid wedge. That's how they represent that one that's poking out at us. The one that's behind us, okay, they represent that by doing a dash. So how do you know when to do a solid wedge and a dash? Well, the solid wedge is if it's poking out at you, so this guy, And then the dashed wedge is the one that's behind the plane of the paper, because you can't see it. It's kind of in line with this guy. They're overshadowing each other. And then for the regular solid lines where no dashes or wedges, those are the ones that are in the same plane. And I mean, for the exam, you're not going to need to draw one of these, but you will need to be able to pick the correct representation given a multiple choice. So this should help with that. But I wanted you to be able to see this. When we do lab 7, molecular geometry lab, this is what we're doing. We are counting valence electrons. We're drawing Lewis structures, and then we're figuring out the geometry of them. And then we're building the molecules. If you come to lab, we'll actually build these molecules. Everyone has their own set. So, all right. That was good for that. I'm trying to think of some other difficult ones. Maybe this will jog my memory. So this is the review. Do you have the sheet? I'll give them a try that. It's just kind of a list of things. How to calculate number of protons, neutrons, and electrons. Everyone seemed to be understanding that pretty clearly. How the periodic table is arranged. That all seems good. Oh, isoelectronic has really been, I think, a confusing topic for a lot of people. So let's try a few of those. And I'm going to start by writing the rules. So for metals, we're looking at isoelectronic. I noticed in the homework and things like that, a lot of people were getting these ones a little confused. So it's different for metals than non-metals. Okay, so metals, they form cations, and they are isoelectronic with the noble gas in the row above. Okay, so for instance, if I'm talking about, let's say rubidium. Rubidium is a metal. It is actually an alkali metal in group 1. So what charge does it like to form? Plus 1. Okay? So, since it's in period 5, that means it's isoelectronic with the gas in the noble gas in the row above. So we're looking at the noble gas in period 4, the row above. So the noble gas in period 4, krypton, Kr. Now nonmetals are different. Nonmetals, they like to gain electrons, so they're going to form anions. And they're isoelectronic with the noble gas in the same row. So, an example of that, let's do selenium, I guess. So selenium is number 34 on your periodic table. It is a nonmetal, so it's going to form a negative charge. It's in group 16, and by group I'm talking about up and down, vertical. So what charge does it like to form? Negative 2, because it's 2 away from having 8 electrons. So if it gains 2 electrons, it'll have 8. So the period it's in is 4. So since it's a nonmetal, it's isoelectronic with the noble gas in the same row. So now we're looking for the noble gas noble gas in period 4, same row. Period 4, period 4. So the noble gas in period 4 is krypton. So metals, you look in the row above. Non-metals, it's the same row. A lot of people with the metals were looking in the same row. I also want to point out the definition of isoelectronic. I know we use that word a lot, and we just kind of find which noble gas and see if the noble gases match. But what isoelectronic means is it means it has the same amount of electrons. So that means their electron configuration are the same. So let's use this definition and try an example using the electron configuration. Okay, so what I mean by that is I'm going to write an electron configuration, and then I'm going to give you a set of choices, and you're going to figure out which pair matches that electron configuration. Okay? So I'm just going to erase this top part, leave the definition down. This might take me a minute because I'm making it up on the fly. So if I give you the electron configuration, 1s2, 2s2, 2, if I give you that electron configuration, say we have there's 1. So out of these 3 sets, what we're looking for is which set has this electron configuration, meaning they have the same electron configuration, so they're isoelectronic. All right. Best way to figure this out is to look and see what noble gas you're talking about. Argon. So 3p6 is argon. And now check out your ions and see if any of them match argon using those rules we just saw. So for the cations, the metals, you're looking at the row above. For the nonmetals, you're looking at the same row.
What about the semi-metals?
Semi-metals,
Because wouldn't magnesium?
Magnesium's a metal because it's in group 2. But like if you had silicon, for instance,
Oh, okay.
so if it's an anion, let's say that instead of a non-metal. If it's an anion with a negative charge, it's the same row.
Okay.
And most metalloids form negative charges. So magnesium. Magnesium's in period 3, so we look in the row above, it's going to match neon. Chlorine matches argon. So chlorine fits, right? It's the same, but magnesium doesn't. So that means this can't be our answer. Because we need both of them to match this electron configuration, which is argon, and they don't because of magnesium. So the next one, sulfur.
Sulfur is
Yep, so sulfur is an anion, so we look in the same row, and that's argon.
argon.
Yep, potassium with a +1, it's a metal, so we're looking in the row above, and that matches argon. So potassium's in row 4, so we look in row 3, argon. So this would be a correct answer, because they both match argon, which is what's represented by this electron configuration. Just for fun, let's check the last one. Calcium, that's also a cation. So this matches argon. What does bromine?
No, it's,
Same row, right? And bromine would be krypton. So that's why this one doesn't work, because bromine doesn't match that electron configuration. All right. Let's try another electron configuration one. It's not going to be with isoelectronic though. It's going to be with ions, because sometimes people have trouble with that too. Because once you have an ion, which means a charged atom, it makes the electron configuration change from its neutral. So you have to figure out, am I adding electrons or am I taking electrons away? So let's write another one here. Okay, so with this electron configuration, I'm going to write some choices, and you're going to tell me what it represents. So, be a choice. All right, so if you have this electron configuration, and I'm saying which atom does it represent? You have some ion choices, you have some neutral choices, and you're just trying to figure it out. So what's going to help you is this last portion here, right? You're saying go in period 2, go in the P block, and it's the 5th one in, if it's neutral. Does this match anything?
fluorine.
So it matches fluorine, okay? So that could be the answer. Does it match any others? So if chlorine has a -1 charge, does that mean it's gaining an electron or losing an electron? Gaining. So chlorine, if I'm following it, let's write the shorthand version of it. So shorthand version, we start with the noble gas in the row above, and then we get to period 3. 3p. So it's usually 3p5 if it's neutral, but we just said we're adding another electron, right? So it's actually 3p6, yes. So this is definitely not matching. What about oxygen with a 2-?
Neon.
It matches neon? Isoelectronic with neon is what you're saying? Yes, so it would be 1s2, 2s2, 2p6. So 2p6 is neon. So it's not the same because this is 2p5, that's 2p6. And then sodium plus. What noble gas does that match with? Neon again, so it's also a 2p6. Okay, so the reason I wanted to do one like this is don't get confused by the charges. Usually when there's a charge, that is its most probable ion, and it's going to match with a noble gas of some sort. Right? All of these match a noble gas. Neon, neon, and this one matches with argon. So sometimes it is just a neutral choice, and we're looking to confuse you with charges.
And what type of example is this? Ion?
Yeah, it would be given the electron, so it would be given the electron configuration. Which atom or ion is represented. And then you would have 4 choices and you'd have to figure out, is it one of the neutral, is it one of the charged? And go from there. So, position of an atom, electron configurations, how to write them given the element or ion, we just looked at that. Noble gas, long way. Electron orbital diagrams, you're not actually drawing one, or even picking one out of a lineup. That was just on the homework, but you do still know those rules, the Aufbau principle. That's the one that says we start filling at the lowest energy level and work our way up. So energy levels, let's look at that. So when we talk about energy levels, and this is back with electron configuration, we have s, p, and d orbitals. So s orbitals are the least in energy, then p, then d have the highest. Okay, so lowest energy to highest. So this is that angular momentum quantum number, right? Where we separated the periodic table. The S's were the alkali and the alkaline earth metals. The P's were the P block over here with the metalloids and nonmetals all the way to the noble gases. The D block are the transition metals in the middle. So S's are lowest, D's are highest. Now, for our principal quantum number, and remember, principal quantum number, those are the numbers on the side of the periodic table, the period that it's in, okay, 1 through 7. So the lowest is going to be 1, and then it just increases as the numbers increase. So on and so forth. So, lowest, highest. So if I were to give you choices, and say, for instance, which orbital has the lowest energy? Okay, so let me think of some choices here. Give those 3 choices. Which one would have the lowest energy? 3S. Why not 2D? It's lower in number.
S is the lowest.
S is the lowest, but there's another reason. Is there a 2D?
No. It's
No.
not 4D.
There is not a 2D. It starts at 3D, so in period 4 you reach the Ds, but the Ds are always 1 less than the period they're in. So you hit period 4, you have the 4 S's, and then the 3 Ds. So there actually is none. So between these two, since they both have the same principal quantum number, you then look at the orbital, the angular quantum number, so S versus P. So S would be the correct choice because it has lower energy than P. I honestly don't know, like if they had like 5S versus 3P, I'm not sure which one would have lowest. So we'll keep it in the realm. You'll be able to figure it out. All right. This was a question from And that's how we fill, so like, see when we're doing our electron configuration, we write it from the lowest energy to the highest. So you can even write out an electron configuration to try to figure it out. Because we would encounter the 2 or the 3s before we encountered the 3p if we kept writing. So that would help as well. So, alpha principle was the lowest energies. That's what made me think of this. Hund's rule was just that you don't pair up electrons unless you have to. That's why when we put them in those spaces, which I know you're not drawing one of these, but when you put them in the orbitals, we would only put 1 electron in each before we started pairing them up. Pauli exclusion principle. That was for each orbital. So if you had a 1s orbital, for instance, the electrons must be paired, meaning 1 up and 1 down. You can't have 2 up and 2 down. They have to have opposite spins, not the same spin. So that's the Pauli exclusion principle, opposite spins. And no more than 2 electrons per orbital. Identify the most probable ion formed. So to identify the most probable ion, you're once again looking at where it is on the periodic table. Group 1 always forms a +1. Group 2 always forms a +2. It's basically how many unpaired valence electrons they have for the nonmetals. So let's look at that example. We looked at nitrogen already when we did Lewis dot structure. So what I'm looking here is the probable ion. So let me write that. Probable ion formed. Kind of weird wording. What they're asking is, if this formed an ion, if nitrogen formed an ion, what would be its charge? What charge would it want to be? And when we're figuring out what charge something's going to be, we're using the octet rule. So everybody wants 8. So you can figure this out in multiple ways. One way is looking where nitrogen is on the periodic table. So it's in group 15. And then counting, okay, how many spots does it need to move to get to a noble gas state? Well, nitrogen, since it's in group 15, has to move 3 spots to be neon. So if it's moving 3 spots, that means it's going to form a -3 charge, will be its most probable ion, because it wants to gain 3 electrons. Another way to look at it is when you draw its Lewis structure. Once again, just like when we're figuring out for covalent how many bonds it's going to form, now we're looking at unpaired electrons for how many it wants to gain. So it, once again, has 3 unpaired electrons, so to get 8, it's going to want to gain 3 more. And if it gains 3 more, that means it's going to have a -3 charge. So you can use these Lewis dot structure to figure out covalently, so covalent meaning sharing, how many bonds it would make, or you can also use them for ionic compounds to figure out what its charge is going to be. So it works both ways. It wants 8, whether it's sharing or taken away and becoming an ion. So whichever way helps you remember it better. Looking where it's at, counting how many to get to noble gas, or actually drawing the Lewis dot structure and seeing how many unpaired for the nonmetals. All right. You can stop me if you think of any questions as I'm just going through. Isoelectronic we talked about. Octet rule, everybody wants 8. Hydrogen and helium are the exceptions. Periodic trends, I think atomic size is all you need to know. Yes.
Can you remind me of the exceptions? I need to know, like boron was heavy with 6.
Oh, for the shapes. Yes. So boron It's basically just boron, actually, because we don't really do aluminum very often because it's a metal. So exceptions to the octet rule. I guess I could start with hydrogen and helium. They just want two. And then boron and aluminum, if he's somehow involved in a covalent compound, which does happen once in a while, is happy with 6 electrons. And then you also have the expanded octet guys. And this just means more than 8. We leave it at more than 8 because sometimes they have 10, sometimes they have 12. So we just say more than 8. And that's anybody in period 3 or higher. And we're talking non-metals, okay? So we're not looking at the metals, so this would be for non-metals. So when I'm talking period 3, we would start at silicon, because it's a metalloid, I should say non-metal and metalloids, sorry. So who can do this? Silicon can do this. Phosphorus and sulfur do it very often. Chlorine can, but we're not going to see it in this course because remember we said chlorine and the other halogens only want one single bond. So we're not going to see them do an expanded octet here, but it can happen. Otherwise, if you just keep going down in period 4, we'll see arsenic do it, we'll see selenium do it, so on and so forth. So most common that we see in this course are phosphorus and sulfur doing an expanded octet. Feeling comfortable with naming or
Yeah.
chemical formulas? There are a lot of practice worksheets.
Yeah, that's what I was looking at now.
Yeah, if you're having trouble with those, I mean, there's answer keys for them, so do those. It's likely that if you have done all the practice sheets, you've probably done every example we could think of. So, Lewis dot we already talked about, valence electrons we talked about. Molecules being polar or non-polar we talked about. Oh, one thing I do want to mention about polarity, because I don't think I said it when we talked about solubility. It's in your book, and I think they asked you a question in the homework. But in regards to solubility, the rule that we looked at was like dissolves like. And we said if you had a polar and a polar, soluble. A non-polar and a non-polar, soluble. But if you had a polar and a non-polar, it was insoluble. Okay, so the reason I want to talk about it now is because I didn't mention ionic at all. All I talked about was covalent compounds. So I want to say that ionic and polar are going to be soluble. Okay, so an example of this, sodium chloride and water. Water is a polar covalent compound, right? We've drawn the shape of it a couple times now. It's bent. It's got 2 lone pairs on the central atom, so it is polar. And then sodium chloride is an ionic compound because it's a metal with a non-metal. So they are soluble in one another as well. The more polar a substance, or the more ionic a substance, the more soluble it is in water. Because water itself is a polar solvent. So if you have polar or ionic, yes, it will dissolve, most likely. 90% of the time. There are a few ionic exceptions that don't work, but for the most part, ionic compounds will dissolve in water. It's the non-polar, so like if we have, a hydrocarbon, these two would be insoluble because we have polar water and non-polar C2H6. But if you have ionic and polar, yes, that works. So I wanted to mention that because I think a lot of people think, oh, these aren't the same, they're not alike, so they're not going to be soluble in one another. And I never mentioned ionic at all, so I did want to bring that up. Ionic can be soluble. in water. It's only the non-polar that's not soluble in the polar. Think oil and water. Oil is a hydrocarbon. It's just carbon and hydrogens together. That's why oil and water don't mix. It's because oil is a non-polar substance and water is a polar substance. Shake it up as much as you want, but they're going to separate back out. And I don't think they really ask you about melting points at all for the exam. But for melting points, if they do, ionic is the highest, then polar, and then non-polar would have the lowest. Ionic would be the highest. Because I sometimes forget about ionic just because we get all wrapped up in all of these Lewis structures and covalent compounds. So ionic still in there. So ionic would have the highest melting points or boiling points, then polar's in the middle, and then non-polar would be the least. And we're going to learn to calculate molar masses later this week, which will also affect melting points. But I was trying to make some molecules earlier. Just for fun, this would be what water looks like.